Hey everybody, it's Ryan. I'm doing my project on antennas. So, what is an antenna? Well, it's simply anything that radiates electromagnetic waves into free space. Or it can be anything that receives electromagnetic waves. And so let's go back to the slide. Here are some examples of antennas. You got the cell phone antennas on the bottom of the title slide, which is, probably the most common thing people would think about. You have the old school antenna down on your left hand bottom part of the page from like your TV. You have this the big satellite dish antenna, and you got even antennas on Wi-Fi routers. So maybe that's not clear. So let's think about an analogy from acoustics that may be a little bit clearer. Um, so you have sound coming out. You're listening to some something that's got some bass to it. And it's just you're listening to something with some heavy bass, and you can see that speaker moving back and forth, and it's putting out a wave, just like this image is showing. So antenna doesn't quite work. It works very similar to that. It doesn't use those physical traits, but it works similar to that. And you can see the image above with the cell phone tower radiating electromagnetic waves. So a speaker radiates sound in the same way as a cell phone tower radiates EM waves. So why should I care about antennas? They seem really boring. And I was right there with you. Uh, why should I care? Well, literally everything that you do that you care about, texting your friends, streaming movies, videos on your phone, using Wi Fi, anything with modern communication is driven in part and a big part by antennas and the capability of those antennas. Uh, we wouldn't be able to get some of the speeds and some of those type of things without good antennas. And so they're pretty important. Well, I guess you could say that's still pretty boring, and I'd give it to you. But hey, um, something that's cool about antennas is they come in all shapes and sizes, and you can actually create antennas on your own. You design an antenna in probably under a day. I mean, even if you didn't know what you were doing, you could find stuff online and probably figure it out in a day or two, and you could probably design in another day or two. So, max, you're looking at a week, and you can make your own antenna yourself. Um, and they have, as like I said, they have all shapes and sizes. And I got a picture right here of somebody making an antenna out of what looks to be parts of stars. So here's some major types of antennas. Um, and I'm going to look at one of them from this list, and one of the other ones I'm looking at is not listed here. But you have the wire dipole, which, going back to the title slide, is an example of the left bottom, although that's an array of that wire dipole. You have the wire monopole, which is what you see here with these the old school cell phones. And you have the the dish reflector, which you see right there in the top left. And the micro patch and corner, I've heard have been used in cell phones. So yeah, you have the horn antenna, which is used to direct the EM wave. So we need to look over some terminology and some antenna terminology as well. So what is frequency? So let's look at this cosine wave here. Um, so you see that frequency is defined by the number of cycles over a period of time. And a cycle is when, in this case, when it goes from zero, um, and it goes to the positive part, and then it goes through the negative part, and then it ends back up at zero, and that's what we call a cycle. So let's take an example. Let's just say our period of time is 2t. We have two cycles, so it would be 2 over 2t, which would just be equal to 1 over t. So we need to talk about resonance frequency briefly. And there's not really an easy way to explain this, but the easiest way is to explain this phenomenon from acoustics. So you may be familiar with a sound wave breaking wine glass. Sometimes they show people singing to do this, but just isn't really feasible. I mean, think maybe you can do it, but anyways, you can use a sound wave from a speaker to break glass without it being very loud, and that happens when the sound wave has this frequency equal to the resonance frequency of the wine glass. And what happens at that resonance frequency is the intermolecular bonds have the least resistance to vibration. So they release a lot of energy because they vibrate really heavily. And so what happens is they end up breaking apart when that happens. So we got this thing called impedance, and without going into too much detail, it's just basically another term for resistance. Wait, so you don't know what resistance is? Okay, that's fine. So you can think about it as water flowing through a pipe, and then that pipe suddenly has a much smaller diameter. Obviously, you can sort of visualize there's going to be some resistance to that flow. Same thing applies to circuits um, and electricity. So we have this thing called impedance mismatch, which from an electrical point of view is when a transition from one part of the circuit to another part of the circuit, and the two parts have different impedances, there's going to be a mismatch. And what I mean, there's going to be a mismatch, there's going to be power that's sent backwards, and power that's sent through. So not all the power is sent from one part to the other part. Well, you can sort of think that that's true if you go back to the pipe example. Some of that water a lot of it's gonna get forced really quickly, and there's gonna be a lot of resistance when it goes through. But some of it won't get forced through, and it'll get pushed back, and that sort of makes sense. So antenna efficiency is just the ratio of power that is radiated by the antenna to the input to the antenna. Um, and so it accounts for losses. So some of the losses are the impedance mismatch that I just talked about, the conduction loss from the metal heating up due to conduction. So uh, heat radiates off and you get loss. You get dielectric loss, which is when the dielectric absorbs some energy when the EM wave travels through it. There's radiation pattern, and I have it's usually a 3D plot of something like field strength or gain or something like that. I have a 2D um, image, or it can be split. Split into a cross-sectional area called the E plane or the H plane, depending on how you do the cross-sectional area. Um, there's something called a beam width. So the region in the direction of maximum radiation, which is the red region in the image, is the main lobe, and the beam width is the size in degrees of the main lobe. Directivity is the degree which radiation is concentrated in a single direction. Is defined as the ratio of power radiated in a given direction to the average radiated power. And gain, that doesn't account for losses, and gain does account for losses, but not for mismatched losses. So you have a half-wave dipole antenna. It's some of the properties of it is it's pretty easy to make. It's cheap to make. It's omnidirectional, lower directivity. Um, Operates best at a single frequency and has pretty low impedance, so it's pretty easy to get a decent match to a coax cable, 50 ohm coax cable. And here is an animated view of the E-plane, and here are the 3D radiation plot. And I have a disc cone here. Disc cone's not the easiest to construct. I created it, took about 6 hours. Still is pretty cheap, created under $50. It's omnidirectional, low directivity. It's wideband, works over a large frequency range. Um, and normally it's used for receiving, not optimized for a particular band for transmitting, and it's not very efficient for transmitting either. Here's some HFSS simulation animations, and the blue shows the E field, and the gain plot is shown right here, and you can see it's changing at the middle. And that's it. Thank you.